Okay, good morning to the course of Green Chemistry Applications for Bioenergy and Bioproducts plants. So, what we will see during this course? Of course, we will speak about energy situation in Italy, in Europe, and all over the world in the last years. What is the trend of bioenergy in Italy and in Europe? Then we will have a look to the energy conversion of biomass. So how can we transform biomass into bioenergy, first of all, and we will see the thermochemical processes, biological processes, physics processes, and the combination also of these processes. Then we will enlarge the vision on biomass transformation because we can transform biomass not only into bioenergy, so of course heat, steam, electricity, and so on, but also in bioproducts. So biomass could be transformed into biofuels, for example, and substitute traditional fossil fuels into the transport sector. And for example, we will see the bioethanol in substitution of gasoline in transport sector, biodiesel in substitution of diesel, biomethane in substitution of methane, and the processes that are behind this pathway. Not only because biomass could be also transformed in other bioproducts, for example, bioplastics, biopolymers in general, for example, natural dyes, which is another important sector we will have a look. And so the idea behind this course is to have a look, to study the biorefinery concept. So if we want to move from fossil fuel system to green system and green world, we have to move from traditional refinery to biorefinery, and so obtain from biomass and from the other renewable energies, of course, to final bioproducts that we need for our society. So this is the scenario of this course. And as I said to you, we have 4 lessons. Okay, every Wednesday morning we have lesson, and the first 3 lessons are dedicated to theory, the theory. In the last lesson, we have to have a small test to verify your knowledge about the course. And then we will move to the laboratories where we have a practical lesson, and we will see some processes applicated into laboratory. So this is the program of the course. Okay. Just another thing. Yes, this is a sort of register, so you can put name and the signature in entrance and in exit. This is today and the other 3 lessons. So, this is the program of the course, and I have shown you just this program. So, the introduction, the energy conversion processes, and of course some practical examples of biomass plants, and first and second generation biofuels, and biorefinery and biochemicals applications. I don't spend many time to show you the difference between renewable and not renewable energies. Just to say that we will speak about biomass, bioenergy, but in a scenario, in a transition from fossil to green energy. Of course, we have to mix all renewable energy, so from energy from wind, energy from water, from solar energy, so photovoltaic and solar energy, geothermal, and a good mix will allow to substitute fossil energy. And of course, we have to cover all energy sectors. Of course, the industry and the civil sector for the production of energy, electricity, heat, steam, but also all the sectors. For example, transport sector is a very important sector that requires a lot of energy, so biofuels are a very important topic to consider. This is a table that shows the trend of renewable energy, of the different renewable energies, the trend in the past, and also the trend for the future. And the most important thing in this table is that bioenergy is quite half of the whole renewable energy sector, both in the past and probably in the future. Yes, biomass is probably the most important renewable energy, and this has a very simple reason. Biomass is the only renewable energy that could be applied in all sectors. For example, you can use wind only for electricity production. You can use photovoltaic system only for electricity production. You can use geothermal only for heat and electricity production. You can use biomass for energy production, of course, but also for the production of biofuels and also the production of bioproducts, biochemicals. So you can substitute the whole refinery with biorefinery. This is the reason of the importance of biomass. But of course, you have to mix all renewable energies to reach important targets for the next years. Of course, make answers to me, so we can have a dialogue, and also you can put some point of view interesting to the lesson. Okay, other graphics that show the importance of biomass, the green part, with the whole renewable energy. You can see that yes, the important is in each country biomass is very, very important. The trend of biofuel sectors, so biofuels is in green, biofuels for transport is in yellow, and electricity is in red. And so another important sector is also yes, house heating, where biomass is growing very quickly. For example, pellet boilers or other kind of biomass. Okay, let me jump to some interesting graphics. This graphic for Europe shows an important event. And you can see that the trend of fossil fuels, also biofuels, and total energy has increased, of course, in the last years. But here you can see a decrease. That, of course, is the period when the crisis in Italy, in Europe, and not only started in 28, 29, and you can see that the crisis means a decrease of energy requirements. Biofuels, okay. These are some pictures showing electricity from renewable energy. This is important, this picture, because shows in each European country the comparison between 2000 and 2012 for renewable energy. And we can see that a lot of countries increased their renewable energy production. In some cases, for example in Germany, the use of renewable energy was the triple in only 12 years. And also in Italy, there was a very important increase in renewable sector. We have doubled the renewable energy in these years. This is also very interesting graphics, because it shows for each country the production of each renewable energy. So, for example, in Italy, we are speaking about electricity, only electricity from renewable energy. For example, in Italy, the hydroelectric production is very important, but we have also to say that this sector started a lot of years ago. So now, where we can use energy from water is just used. So it's a very slow increase in this kind of renewable energy. Solar sector also increased a lot. Geothermal is another important renewable energy, but just used where is economically there is economical convenience to use. And also biomass is increasing in electricity production. And you can see also the other European situation that of course depend also on the geographical situation of each country. For example, Sweden has 80% of renewable energy from water, because there are a lot of lakes and rivers. Or the same in Austria, where there are a lot of mountain lakes to use. And these are some characteristics. For example, Germany, Holland, Belgium, where that are in front of Northern Sea. They have a lot of wind, so there is a lot of renewable energy from wind. It depends also on not only on political choices, but on geographical situation. In Italy, this is the trend of renewable energy in the last years. So there is an important increase of renewable energy in these years, and it depends on the economic incentives that our country gives to renewable energies. Now the trend is going, the increase is slowly, because a lot of incentives are finished, and so it means that there are less new renewable energy plants. This is the production of renewable energy in the last years, yes, in the different renewable energies. So as I said to you, geothermal is very flat line, because we built a geothermal plant, yes, in the past century. So the production is very constant. Also, hydroelectric is very constant. The difference in each year in hydroelectric system, we are speaking about a gigawatt hour, so energy. And energy depends in hydroelectric on how many rain we had in a year. So the trend depends on the rain of each year, because of course the rain goes to rivers and goes to lakes, so increase or decrease the energy production. The photovoltaic energy has a very, very high growth in the period where incentives were very high. So we have an important increase. Also biomass has an increase, but very constant. And this is the situation of energy production. And also here a decrease that depends mainly on the rain, not on the decrease of renewable energy production. So the trend is increasing. Okay, and the renewable energy production compared with the whole energy production in Italy, the renewable energy cover between 37 and 40% of total. So actually we have 40% of electricity from renewable energy and 60% from fossil fuels. This is another table that shows the situation, and here, of course, the comparison between green energy, renewable energy, and the other fossil fuels. We still have a lot of methane. We still have other kind of fossil fuels, and we still have mi sfugge la coal in inglese. Coal. Thank you. We still have a lot of coal that produce energy with environmental connected problems. Yes, these are similar pictures and table. Here are some characteristic of biomass or other renewable energy plants compared with the sites. And here you can see that, for example, the blue one should be, yes, for example, for geothermal, all plants are more than 1 megawatt, okay, of course. And for example, the biomass situation is not so particular. We have different sites, and depends on the typology of biomass system. The same for hydraulic. From wind, of course, we have little plants. For example, for biogas, the most part of biogas plants are from 200 kilowatt to 1 megawatt, and it depends on the incentive mechanism that that give a higher incentive to this kind of sites from biogas plant. Renewable situation by region, of course, the production depends also on the typology of renewable energy we use. For example, in the north of Italy, we have a lot of energy from mountain lakes, and so you can see that the whole renewable production is very high. Regarding photovoltaics, this is the trend of the last years, and you can see that there is an exponential growth due to very good economical incentives to these plants. And yes, you can see on yellow line the size of the plant, and on the gray line the number of plants. And you can see that from 30,000 we moved to close to 1 million plants in Italy. And so that is a very important growth. This is a little strange picture, because as you see, the energy from photovoltaic, the energy from sun increase going to the close to equator, and in this case the higher production of photovoltaics is in the north of Italy. But yes, it depends also on politically reasons. So it's very long to to explain. Wind trend. It's increasing. Energy. This is the number of plant in gray, and the size of plant, and here the energy production from wind. The position, the position of plants in Italy, and this is, I think, it's correct, because we have a lot of wind in the south of Italy and in the main islands, so it's correct. Hydroelectric, yes, as I said, here you can see, yes, the installed megawatt in Italy, and you can see that it's very constant. There is a very small growth due to very little plants, and you can see this because the megawatt are 17 to 18, so the growth is very low, but the number of plants in gray moved from 2000 to mainly 4,000. So it means that we have a growth of very small plants, and this is the reason I told you some minutes ago. The most important sites were just used, and we have just built plants in the past. So we can only use, for example, the small jump in rivers or lakes. So small plants, all these small plants that are important, are very important, but don't move the global situation. And hydroelectric, of course, is very developed in the north of Italy, thanks to the demographic situation. Okay. Geothermal, as I said you, the number of plants is the same, 34. Sometimes is lower because some plants are very old, so they need to be rebuilt. So the number of plants is 34. Where we can use geothermal energy, we just have a plant. So no more possibility. There is no economical feasibility to the realization of new plants. Here, where they are located, the geothermal plants, very close to our region. Okay, this is the biomass trend. In general, you can see in brown the power, which has increased a lot in these years from 2008 to 2013, where there was an interesting incentive, and the number of plants, yes, we are very close to 3,000 biomass plants. We are speaking about electricity production from biomass. Okay? Here you can just see some typologies of biomass plant, because we have, for example, in dark violet biogas systems, in light violet bioliquids, so liquid biomass, and other biomass in pink. It means solid biomass, so for example chips, pellet, or something like that. And this one is wastes, but it's not the goal of this course. We will not speak about wastes. Okay, this is the regional situation. Of course, our region is very small, and the biogas sector is not so developed. Only biogas has had a good development, and some solid biomass plants, but very slow, very low development. Okay, this is the regional distribution. I can jump some pictures. Yes, this is another important topic. Bioliquids. I mean, when I speak about bioliquids, I mean mainly vegetable oil. So, for example, the oil that we can obtain from the seeds milling. For example, sunflower milling, for example, different kind, for example, yes, palm oil, soybean oil, and so on. So this is the bioliquid situation in Italy, and of course you can see that the main part of oil comes from palm oil, and of course we can't cultivate palm in Italy, so of course this biomass comes from the other part of the world, and so there are some problems with the sustainability of this biomass. For this reason, the economic incentives for these biomass plants that started for every kind of biomass changed, and actually we can have an incentive, economic incentive only if we use European oil, because yes, there is no sustainability to import oil palm from 4,000 or 5,000 kilometers from here. Okay. Yes, this is the production of oil, and you can see that palm oil comes from Indonesia and Malaysia. In Italy we have sunflower and similar cultivar. Or other derived vegetable oil. Okay, this is the last picture about energy trend in Italy and in Europe, and it's the electric balance in Italy. And here you can see the production of energy, and on the right side you can see the final use of energy. And it's interesting to compare renewable energy, hydroelectric, bioenergy, geothermal, wind, solar, not renewable, from coal, natural gas or other plants, the import of electricity. We import 12% of electricity, and a very important part of this imported energy is from nuclear energy, for example, from France, from the East countries, and so on. And then we have the final use, where yes, the main, the most important sector is the industrial sector, that use the 42% of energy, the tertiary sector that use the 35%, and then of course house energy consumption, and a very little part for agriculture. Okay? And just to have a number, this is the total request in Italy, approximately more than 300 terawatt hours. So 1 terawatt hour is 1,000 gigawatt hours. So this is equivalent to 300,000 gigawatt hours. Okay, this is the national electricity request of the grid, the Italian grid. Okay. this is a table that shows the situation on the transport sector. So we have spoken about mainly about energy consumption and mainly about electricity consumption. This is a situation about transport sector, and in the blue line you can see the total energy consumption in Italy for transport sector, and we are 44 megatore, okay, tons oil equivalent. Of course, so 1 million, 1 megatore is 1 million tons oil equivalent. And so in Italy the trend is from 44 to 40 megatore. Okay, it's clear? And what we use to in the transport sector, of course we use fossil fuel products in the main part. Yes, you can see we are more than 90%. We use, of course, diesel, gas line, of course, jet fuel for the flights, and methane for some cars, and we are starting to introduce biofuels into fuels, and you can see mainly biodiesel. We don't have bioethanol still, so biodiesel mainly, and of course some electricity from renewable, of course, because as we have seen a few slides ago, if we have 40% of electricity from renewable energy, of course this 40% also can reach the transport sector, because electric cars are starting to grow. Okay? And here you can see also the percentage of each product, and for example for biofuels we are less than 3%, and another 1% of renewable energy comes from electricity. So in total we are 3.5%. We have 3.5% of renewable energy in transport sector, and so you can see that it's the more important sector to reach using renewable energies, because in the electricity sector we are at 40%, and here we are at 3.5%. So it's the more important sector for the next year challenges. Okay. Any question on this part? Okay, if you don't have questions, we can move to after this introduction part, we can move to biomass. So we'll have a look to the definition of biomass for our law, and then we move to processes. Okay. This is a very simple slide to show the reason of why biomass is a renewable energy, because this is the reaction in each vegetable that from CO2, from carbon dioxide, from water, yes, using solar energy, the vegetable, the plant transform carbon dioxide and water into sugars and then into polymers that hello the plant grow up. Okay, and I sometimes I have this question. Also, for example, fossil fuel are yes, derived from biomass because methane or oil or coal are vegetable that yes that receive high temperatures, high pressures, and they transform into fossil fuels. So why biomass is a renewable energy and coal isn't a renewable energy?
Because coal and other fossil fuels over time they deplete, and the production of those fossil fuels versus the consumption of the fossil fuels is not balanced. It's like if we use 1 ton of fuel in a year, but to produce that 1 ton, it requires like at least 1,000 years of decomposition, pressurization, and everything. But in case of biomass, it keeps on coming and you can keep on transforming. It's a constant cycle.
Yeah.
So there's no break.
Perfect. Okay, this is the answer, the perfect answer. Time is the yes, is the difference between biomass and the fossil fuel energy. If we have lived in the Stone Age, probably fossil fuel could be considered a renewable energy because the energy we need is slower than the time of regeneration of fossil fuel energy. So this is the reason. If we use biomass respecting the growth of plant, we can call it renewable energy. But if we use biomass, all the biomass, all the plants in the world in 1 year, it's not a renewable way to use biomass. So it's time. The time is the most important thing. Okay, very good. So another very elementary picture that that show also why the bioenergy has a zero carbon dioxide balance. Because when we burn biomass, we produce carbon dioxide. Every thermochemical but also biological reaction produce, of course, carbon dioxide. The reason of a zero balance is that the carbon dioxide we produce and that goes to the atmosphere is the same carbon dioxide that the plant used during its growth. So if we respect the growth cycle in the biomass in the plants, we can consider a balance, a zero balance. Okay, and of course, I think you know very well the carbon dioxide is the most important greenhouse gas greenhouse gas for atmosphere that yes, that modify the energy balance of our system we are considering, because it create yes, a greenhouse effect that block the energy re-emitted from our Earth, and so in global the trend is to grow the temperature. So the effect is to increase the energy inside the system, and so the effect is to have an increase of temperature in the last centuries. Okay, just a look to the definition of biomass. This one. I will try to translate it in English. So, in Italy, what we consider biomass? Biomass is the biodegradable fraction of product, waste and residues which has a biologic origin, coming from agriculture, forestry maintenance and connected industries, and also residues from parks, both public and private, and also the organic part of wastes. So this is the definition. So I repeat, changing the words. So we are speaking about the biologic, the organic fraction of biomass coming from agriculture, and so we mean energy crops. Okay, then we speak about energy crops, and also residues from agriculture. And so, for example, vineyard residues, olive residues, fruit trees residues, straw, for example, and so on. Biomass is also the forestry maintenance. So when we maintain forestry and we have to cut trees every 20-25 years, the wood and the other part of the plant are considered biomass. And also the connected industries. And so, for example, the production of beer have some residues from the production, and this is biomass. The production of wine has some residues from the grapes milling, and this is considered biomass, and so on. We will a lot of slides that show some examples. Yes, the residues from public and private parks or gardens, and so this is considered biomass. And finally, a part of wastes, so we don't speak about wastes in general, but the biodegradable part of wastes is considered a biomass, and it's mainly used for biogas production. Okay? Then we have other terms that we use from the national law. For example, we speak about bioliquids when a liquid biomass is used for the production of electricity or heat. We speak about biofuels, so bioliquids and biofuels when the liquid biomass is used for transport sector, with biodiesel and bioethanol. We speak about biomethane when, yes, it's methane, a chemical formula of CH4, but obtained from biomass. These are the main terms we use, so I don't lose time to show you this. So, the definition of biomass defines also some sectors where we can obtain biomass. Forestry sector, as I just said, energy crops, industrial sector. This should be the residue of grapes milling. In Italy we name it vinaccia. I don't know the grapes residues in English. Agricultural sector and zootechnical sector. Also the residues from zootechnical sector. We usually divide the biomass into three pathways. Energy crops. So we have from 5 sectors we have reduced it into 3 pathways. Energy crops, biomass residues, and biomass from agro-industrial and zootechnical sector. Okay? And these are some examples of the 3 pathways. For example, energy crops, we have biomass from short rotation forestry, so plants that has a very quick growth. For example, poplar, robinia, and in this kind of trees grows up into 2, 3, 4 years. They are just ready to be cut and to produce biomass. Another kind of energy crop is oil crops. For example, sunflower, soy, jatropha, palm, and so on. This is alcohol crops. For example, sorghum, grain, and so on. And yes, grass crops that we can use also for energy production. Residues from agriculture and forestry, and here the example just made, and the residues from agro-industrial and zootechnical. For example, also the residues of milk production is will be used for bioenergy production. The cover of rice, of course, will be used for bioenergy purposes, and so several examples of biomass. Okay, I go on. These, from now there are a lot of slides that show many kind of biomass. I try to go very fast because I prefer to move towards energy processes. So we have a look. I stop when there is something interesting, but we can go on. You can see energy crops, poplar, eucalyptus, grass crops. Here I stop because I would like to spend 2 minutes speaking about cardoon in English, or sometimes black locust is the term, but we usually use cardoon. It's an herbaceous plant that in some varieties grows up to 3 meters tall, and it's something like an artichoke, okay, very, very tall artichoke. So we have a lignocellulosic part we can use for energy purposes, and then we have the flower, similar to artichoke, and in the flower, yeah, there are the seeds. So if we collect these seeds, we obtain vegetable oil that can be used for a lot of purposes, from biofuels to bioplastics to bioherbicides to biolubricant. So it's a very, very important potential. And we just have 2 or 3 research projects, national research projects, to develop the pathway of cardoon from the field to the final bioproducts. And I will show you some slides in the next lessons. Okay? And this is very interesting because you can produce both a lignocellulosic part, and we are speaking about 15, 16 tons per hectare of lignocellulosic biomass, and also approximately 500-600 liters of vegetable oil, and also the residues of seeds milling is another important part, 1 tons, more than 1 tons per hectare, that can be used for animal feeding. So we have a crop with a lot of applications, and we are speaking about a crop that don't need water, that grows up in very, very bad fields. We tested it into very poor fields, and it grows up very well and don't need the water. So it's sufficient sufficient rain. Also in some area where the rain is very, very low. We tested it in the north of Sardinia, which is one of the 2 main islands of Italy, and there we have not more than 400 millimeters of waters of rain each year, and the biomass grows up, the plant grows up very, very well. So it's very interesting biomass because don't require many water, don't require good fields, don't require agricultural treatments, and has a very, very good production of biomass in different typologies, and so different final bioproducts. So in an idea of biorefinery, it's a very interesting biomass. Okay. Yes, just to complete the vision of this energy crop. In Italy and also in Europe, energy crops are not the solution of energy problems, because energy crops go in competition with the food crops. So if you go in competition with food crops, you have a problem of price increasing in food products, and competition competition and so on. So in Italy and also in Europe, we are abandoning energy crops, this kind of energy crops. Cardoon is very interesting because you don't need food crops. We don't need food fields because for food agriculture you need good field with water, with nutrients and so on. Here we use we name it marginal fields that are not used from agriculture, traditional agriculture. So it's another good solution to not go in competition with food agriculture. It's okay. Other kinds of energy crops. Sorghum, miscanthus, cardoon, okay. Trees, poplar, but I repeat that these crops are going to be substituted with other residues, and here you can see all the typologies of residues. Yes, from grain, residues from grain, from straw, different typologies of straw, from rice, rice straw, from maize, the vineyard prunings from vineyards, pruning from olives, pruning from apple, pear, and so on. Sunflower residues, so the lignocellulosic part of sunflower, not used for food production, and the residues from agro industry and zootechnic. Okay, this is the panoramic of biomass. Then we have to transform biomass, the biomass you have seen, into a biofuel. And so these are some examples of solid biofuels. Of course, we will speak also about liquid and gaseous biofuels. But these are some examples of solid biofuels. So you start from straw, from a pruning, from a part of a tree, and you have to transform it into biofuel that can be used for an energy system. Okay? And so, yes, you can transform it, for example, into chips, which are small chips you can use into a boiler, for example. You can use, of course, also sawdust directly, but in general you transform sawdust into pellet. Pellet are some small cylinders that you can use in pellet boilers for domestic heating, and these are the most important biofuels. Of course, you can use also wood for domestic use, of course, not for industrial use. For industrial use, you have mainly wood chips that are not so expensive to produce and have a good versatility to be used in a lot of thermochemical systems. Okay, this is sawdust or residue of wood production, and these are pellet or briquettes, which is another typology of biofuel, and of course these biofuels are only for domestic use. It has no sense to produce electricity from pellet because the production costs of pellet are very high, so it's good only for domestic use where you need a very a biofuel with a high energy content, because high energy content means less space that you need to store pellet, very low ashes content, and this means that you have to maintain the pellet boiler every 2 months and not every 2 weeks, and so on. So it has sense only for domestic use. Okay, these are some pictures about the use of several biofuels solid biofuels in Italy, and so this is wood chips mainly for industrial use, and this is the use of pellet, not only in Italy but here in the world. So pellet has very important development in the world, because it's a good fuel, a good biofuel for, I repeat, for domestic use, because of the reason I said you.
Excuse me. The pellets, they are just made from like a certain kind of feed, or like are they the pellets for any kind of organic material? Like the one you showed, it looked like it's just made from wood.
Yes.
Are there any other kind of pellets that's being used?
Okay, the economic convenience of producing pellet, if you just have sawdust from wood industry. So it has no sense to start from wood, transform it into sawdust and use a lot of energy, and then create a cylinder with high energy. So the pellet derives only from food, from forestries, but if you have a good industrial sector where we have a lot of sawdust, which is a waste for you, and so you transform waste into a product.
No, I understand, like the pellets that you showed, they are from sawdust,
yeah,
and like the other process, but are there any other pellets, suppose like dried agricultural waste, like after you cut the crops and you have a lot of hay and everything, the husk that we talked about, the covers for seeds of wheat or rice, or suppose from wine industry, the grape mush, can you dry that and create pellets? Is it because
it's not so convenient?
Because of its low energy value, or just like too
both
much
both energy value and also energy that you spend for these processes there, because dry a very wet biomass has a large cost. Transforming it has a large cost. In our researches, we are testing several kind of pellet from agricultural residues or something like that. But the problem is the economic convenience, because too much processes means
Like
too much.
economics, like in drying and conversion and everything.
Yes. For
becomes-
example, you mentioned waste from wine, from grapes. In this case, you have 90% of water, so it's very not so convenient. If you can, it's better to use it into biogas production, where water is not a problem. So, but it's an opportunity. So, in some researches, we are testing some products that.
Like taking, I understand drying in general process, its energy consumption is the main issue, and since we are solving the energy, it's a cyclic process. But is there a possibility of using solar dryers?
Of course, yes.
Because I've seen some instances where they like waste from tomatoes, like after they are using the ketchup and those kind of industries. They sun dry it or use solar heaters and everything, and then that is converted into feed for animals.
Yeah.
But can that be used for no?
Of course. It depends on the value you obtain for the final product. So we have still not spoken about other reasons. But for example, in these agricultural residues, you have a lot of ashes. So you have a final product which has, for example, 4 or 5% of ashes, and pellet has 0.1% of ashes from wood. And so it means that you produce 50 times ashes, and for domestic use it's not so convenient, because my father or my mother has to put away ashes every 2 days instead of every 2 months. So there are a lot of reasons behind this possibility. Pellet yes, is used only in domestic houses, so it has must have very good thermochemical characteristics, so economical and thermochemical characteristics. So these two things are very difficult to obtain from other than sawdust from.
So cost and calorific value of any feed is at the most.
Yeah. Yes. But research probably could help us to accept from this trend. Okay, this is the market of pellet in the world, in Europe, and divided from country. And yes, another important thing, you can see the data is old, but is useful to understand some things. Here you can see for each country, in red the production of pellet, and in blue the consumption of pellet. And for example, in Italy you can see that we have a consumption 3 times of the pellet we can produce, because we don't have so many food industries to cover the market request, and so we have to import pellet from Europe or from all over the world. And so it's another problem, because we will see during this course that bioenergy from biomass has sense if you shorten the travel from biomass to final bio product. And so if you import palm oil from Malaysia, it has no sense both environmental and energy and economical point of view. And so you have to, yes, to produce biomass here and to transform it into energy 50 kilometers far away from here, not 5,000 kilometers. Okay, and this is a very important reason. For example, the pellet is not considered so environmental friendly because, of course, a large part of pellet is imported from Europe or from all over the world. Because I should have another slide that shows where pellet come from to reach Italy. And okay, Austria is very close to Italy, Germany is very close to Italy, but Romania, Lithuania, Canada is very, very far away. Egypt, Ukraine, so it's a good biofuel, but not so environmental friendly. So it depends on the life cycle analysis, but it's an evidence that if you have a long travel, you lose a lot of renewable inside the product. Okay, I don't know if I jumped some. Okay. This is the pellet boiler or pellet grooves in market in Italy, and you can see that the growth is very important. This is a very particular growth due to an incentive that in 2006 was very interesting, and so the market exploded. But the trend is, however, very, very good growth. Okay, because it's a very comfortable system for domestic use. Okay. So now, we'll start a part that regards the main thermochemical characteristic of biomass that are important to study in each process, and also we will have a look to what laboratory instrument can be used to measure this characteristic. Okay, this picture just to show you the three main part of every typology of biomass. So in this picture you can see a wood biomass, but the concept is the same in every typology. We have a percentage of water, of course, and water means moisture, which is the characteristic that describes the water content in the biomass. In general, we have the organic matter, and then this means that in general is the part we can convert into energy, and an inorganic matter when we have a thermochemical process, but in general we find it at the end of the process. If we have a thermochemical process, we find this part into ashes, and so this is the three main parts of biomass. The organic matter is in general carbon, hydrogen, and oxygen, which create polymers cellulose, semicellulose, lignin, and other polymers, but also some other elements, nitrogen, chlorine, and sulfur, that are associated to pollutants. So pollutants, or an element that with an oxidation transforms into a potential pollutant. And so, on the highest part of the slide, you can see the potential in terms of energy, but also in terms of final byproduct, because we have to read this picture not only for energy purposes. In the lower part, you can see in general the problems connected with these elements in terms of corrosion, but also the environmental problems in terms of emissions into the atmospheres, and so the systems can reduce this emission. Okay. And the same is for the inorganic part, which is ashes or very little molecules that cannot be collected as ashes, but follows the exhausted gas and goes into atmosphere. And I'm speaking about particular matter. The same thing can be read with this line where you can see the fraction that can burn, and here you have carbon, hydrogen, oxygen, nitrogen, and the other we have seen into the organic part, ashes and water. Why this slide? Because when we speak about chemical physics characteristic of biomass, we can use different terms. Okay, we can speak about the sample, the biomass, as received. Okay, and so we can see that, for example, the sample has content of carbon of 50% as received. As received means that we are considering the whole fraction, the complete fraction, so the complete part of biomass. So 50% of this quantity as received in Italian come ricevuto. But since the water is a very variable part of biomass, we can very often we can speak about dry basic. So, for example, in the same example like earlier, we can say that biomass has 60% of carbon dry basis. 6% is referred to the dry basis, so the fraction without water. Okay, it's important to specify where is the received that characteristics. Or we can also express that characteristic on dry ash-free basis in English, DAFB. So we are referring to only this part, so without water and without ashes. So for example, the content of carbon is 60% or 50% dry ash-free basis. So refer only to this fraction, the organic fraction. Okay? And it's very important because every expression has a different meaning. For the reason I told you, water is a part that can be 5% of water, 5% of moisture, and in this case it's not so different speaking about the as received or dry basis. But if water is 50%, and sometimes happens, it's very different to speak about as received and dry basis. There is a very large difference, and so this is the reason we use in a very in many cases we use dry basis, so to exclude the influence of water content or moisture. It's okay. Okay, this is the scene. So, what are the most important parameters that we use to describe biomass characteristics? Of course, we have just introduced moisture and ashes content, and these are a very important part of biomass. The part we name substance that during a thermochemical process transforms into gas products, and this is this parameter. The content of carbon, hydrogen and nitrogen, of course, and we also just introduced these parameters. Heating value, and we speak about low and high heating value. Okay. This is a parameter that we use only for pellet, and is the mechanical durability of pellet, that describe the capacity of pellet to not turn back into sawdust during moving, transport, and so on. And then we have also a lot of macro or micro elements, for example, metals, iron, vanadium, or other elements like sulfur, chlorine, and so on. And finally, the fusibility of ashes. I don't read this parameter because we don't have in laboratory the instrument, but the temperature of different phase changing of ashes is very important, because of course when you for example reach the temperature that some ashes pass from solid to liquid, is very dangerous, because they liquefies, but after when the temperature goes down, they turn back to solid state, and it's very dangerous for the mechanical part of the boiler, of the system, and so on. So it's another very important characteristic.
Excuse me.
Yes.
You said that ashes here, they change their phase with temperature. What temperature do you operate in these conditions that they change?
It depends on of what elements are in ashes. For example, I can make you an important example. This silicium has a very low fusion temperature. So if you have a lot of silicium in ashes, for example from herbaceous biomass, you have a lot of silicium, the fusion temperature goes down, and it's possible to reach this temperature during a thermochemical process, during a combustion, for example, because you can also have temperature between fusion temperature between 300 degrees, 350 degrees, so low fusion temperatures, and it's a very important problem because when you after the fusion you turn back to solid phase, there is a particular solid state which is I don't know, the ashes turn back like something of glass. Vitrification. And I was not sure it was the correct term in English. And so you have yes, you can destroy the boiler or where they have turned back to.
But in some cases, like some studies, those kind of ashes or the fusion process is very beneficial then.
Yes, of course. Of course. I
because-
was referring to domestic or something like that case where we don't need to vitrify ashes to obtain.
Because in terms of environmental impact, a vitrified ash is much more stable and
Yeah,
it can.
yes, of course.
There's no leaching or.
In an industrial situation, is sometimes it's good to transform to vitrify ashes. Also for some applications that you can have for ashes. But yes, the example was on the negative side when you have a domestic case and you vitrify, for example, in the system that move ashes, for example, a straw, and you can also
Because this might
change with a new one straw
because this might be out of the topic. Like we were trying to vitrify a lot of ash in order to stabilize because we wanted a vitrified ash. So it's interesting to see that here that is a problem.
Yes, yes, of course.
And that's it.
Okay, thank you. So, of course, we don't have time to to go to see on detail every instrument, but we have a characterization laboratory downstairs, and we also have a look on the last lesson to this laboratory, where we have the instrument that can measure the parameters I've introduced you. For example, then more detailed look, the thermogravimetric analyzer, which is a system that can measure moisture, ashes, and volatile part. The calorimeter to measure, of course, the heating value of biomass. The system, the elementary analyzer for the content of carbon, hydrogen, and nitrogen. The system for the durability, pellet durability measure, and ionic chromatography for chlorine and sulfur measure. We also have other instruments that are not in this list. For example, we have ECP, optical ECP, for the analysis of metals content. We have several chromatographers for the analysis of sugars, or for some alcohols, or other substances. So it's not a complete list of instruments, but of course we have the possibility to see it directly in the laboratory. Just a look to, for example, to the thermogravimetrics analyzer. This one is a sort of stove where we put the sample, a stool with a balance, and yes, this is the open instrument where we have rotating balance, where we put the samples. We have, I think, 15, 20 samples to put in one cycle. Okay, what we do? We prepare, of course, the sample, and we will see the preparation part. We put the sample inside, we close, and we at the beginning we move to 105 degrees. So this is a temperature that allows to water to vaporize and to go away. And so the balance measure the weight change, and automatically can give you the information about moisture, because the difference between the initial and final weight gives you the moisture content of the sample. And then I don't have the complete scheme. Then we put the temperature up to I think 800 or 900 degrees, something like that, in order to without nitrogen, so we don't have a combustion, but we have only the volatile substance that go away, and we can measure that one. Finally, at a lower temperature, 400, 500 degrees, we put. I told you without nitrogen, and with nitrogen, of course. So the system is completely without oxygen. I want to say. So we don't have combustion. We have only nitrogen. We don't have combustion. The final step is at 300, 400 degrees centigrade with air, with oxygen, and so the combustion is complete, and you find only ashes at the end of the process, and with the balance we can measure ashes content, volatile substance, and also fixed carbon. So you have with these double passages from when you put away volatiles, you have ashes and fixed carbon. When you have combustion, you lose the carbon part and you have only ashes. And so you can measure these four elements. If you make a sum of this percentage, you should obtain 100%, approximately 100%. Okay? So just to have a look to moisture, we have mentioned various times. You can see that moisture could be also 50%. Also 70%. If you collect, for example, maize, when you collect him, you should have 70% of moisture. But in general, when you speak about lignocellulosic biomass, you can have a moisture from 50 to close to 0%. It depends on the characteristics of biomass. For example, wood chips, some are very often close to 40–50% of moisture. Wood, dry wood is 20%. Pellet is under 10% of moisture, and so is the reason it has a high energy content, because in this table you can see that there is a direct proportionality between moisture and energy content. Of course, if you have less water, you have more energy from the other parts of the biomass, and if you have water, you have more water, is less organic matter that can be transformed into energy. Okay. These are some typical values of ashes content for different kind of biomass. For example, herbaceous biomass has a very high content of ashes. For example, straw, cereals, or rice. This is not the rice, but the rice husk, bagasse, and so on. In wood from forestries, this percentage goes down. And for example, from sawdust, which is the part you use for pellet production, we have a very, very low ash content, under 1%, and in many cases also 0.5. Okay. These are some formula for the calculation of moisture, ashes, and fixed carbon content. And this is the software that show how you work during this process. For example, here you can see on the left part the weight loss in percentage connected with temperature, which is the red line. So weight loss is the blue line. Red line is the temperature, and you can see that you have a first stage, this one, you are at 105 degrees, okay? Then you go to 900 degrees, and then you go to 400–500 degrees for the part. And here you can see the weight loss. That means this weight loss means is weight loss when you reach the correct weight loss. It means moisture. This one means volatile substances. This one means carbon, fixed carbon, and then the final, the ashes. Okay? And here you can see also the time. One cycle depends on the biomass characteristics, but is 5, sometimes 6, 7, 8 hours, because you have to wait until there is no difference of weight between in some minutes. So we have to wait. The loss may lead to makes all water goes away from the sample. Okay. Okay. There are also the values. For example, this is a pellet sample where we have 1% of ashes content. I'm not sure, but of course this is as received, and this is dry basis probably. You agree? Okay, because the moisture is 10%, so it's very reasonable that this is ash dry. Okay, I know. So ash dry basis and ash as received, and the same volatile and the same fixed carbon. So you can read what in the two most used way. In this case, the difference between dry basis and dry ash-free basis is very, very low because ash content is 1%. So the difference is very close to 1% between these two ways. Okay, this is the same characteristic. Then we have the elementary analyzer, which is a gas chromatographer. So what we do, we burn the sample, we put into the machine, and we and the system read the gases you obtain. So you read nitrogen dioxide, carbon dioxide, and water, gas water you obtain, and the system read how many of this component you have, and you then transform it into percentage. So, for example, this material, I'm not sure, but should be PO in our nomenclature, is olive prunings. So, for example, in the olive prunings you have 22% of carbon, which is very low, very, very low. 6% of hydrogen and 5% of nitrogen. Okay?
Sorry, one question. So this machine is a gas chromatograph?
Yes.
And it can read the water percentage, the water content?
Yes.
By condensing it and weighing it?
No,
in the vapor phase?
Yes. Heating value, and of course we have to make a difference between low and high heating value, and of course it depends on the water that you have in the biomass, because water is not only an element that substitutes the burning part, but if you have a thermochemical process, water at combustion temperatures, so of course more than 100 degrees, has a phase change, and put away some energy from the system, which is the energy to pass from liquid to gas. And so this difference can be considered distinguishing low and high heating value. The system, the machine that measure the heating value, then you can move from low to high heating value using some very simple formula. The system is the calorimeter, which is a system where you create with oxygen a pressure, a very, very high pressure. I'm not sure, but we are speaking about several bar. So it's called Mahler bomb because the pressure is very, very high. And then here you can see electric resistance, and you put the sample, the prepared sample here. You close the system, you put the system into this one in completely covered by water, okay, with the system to move water and uniform the temperature. What happens? When you are ready, the resistance, yes, of course, create the way to start the combustion. We have oxygen, we have biomass, which is our fuel. We have the electricity to start the combustion. We have a complete combustion of biomass. Okay, this is energy production that increase the temperature of water. So you measure the different of temperatures, and using the calorimetry law you can obtain, of course, the energy content of biomass. Okay, this is the Mahler bomb, and of course this is the correlation with the capacity of the calorimeter, and this is the relation that take in account also, of course, there is some part of plastic that burn, and so there are some terms you can correct the formula to don't take in consideration that the contribute of that one. Okay, and these are some low heating value of some fuels and biofuels, and you can have also a comparison between the fuels and biofuels. Here you can see the kilocalories per kilogram, and if you have a gas fuel, you can see kilocalories for cubic meter. Okay, or the variation, because here wood is from 2,500 kilocalories per kilograms to 4,500 of kilocalories. Okay, and here the expression with other measuring it. Okay, so wood compared to, for example, coal. Of course, fossil fuels have as a higher low heating value. For example, diesel, gasoline, and methane. Of course, biomass has a lower energy content, and this is the reason because you can't move biomass for long distances, because you lose a lot of energy, because the energy in volume is very low. This is the ionic chromatographer. Then we have also liquid chromatographer, but I don't know that, yes. In 2 words, you are chemical engineering, so it's very simple for you. But in 2 words, the chromatography is chemical techniques that allow to, if you have something, a sample to measure, it's a techniques that allow to separate components in function of the affinity they have with the material of the column. So you change the column in function of your sample, and yes, you have a mix of more component. When you put it into the column, they go quickly or no if, in function of their affinity, more less or more affinity with the column, and at the end of the column you see the components in different times, and so you can associate an element or a chemical element in function of the time and of course you can also measure the quantity of this element. Sorry for the not so good explanation, but this is another picture that shows if you have a sample with 2 elements, for of course for simplify A and B, the column during the column they goes down, they start to separate. Of course, B has more affinity than A, and so they goes down, and so at the end of the column you see the components in different time separates, and here is the chromatographer. You can see in time, and here A with of course the area of this one is the quantity of component A, and then component B. Of course there is a lot of work to associate of course a time with a particular elements, and we use it for example for ionic chromatography, that yes, you use the positive or negative characteristic of some element, or liquid chromatography. For example, we use liquid chromatography for sugar measurement, for alcohol measurement, while we use ionic chromatography for chlorine and so forth measurement. Okay. And this is the, for example, the results of the our ionic chromatographer. Oh, the last parameter I've shown you is the mechanical durability of pellet. So we use this parameter only to describe not the biomass in general, but only pellet. And it's very simple. It's a very simple system. I don't know if I have the figure. Yes, okay. You weight the pellet you put inside the system here. You put it inside here. There is a system that moves very strong the sample, and of course a part of pellet will break down and transform it into sawdust. There is a grid with some holes, so sawdust goes down in the system, and you weight the sawdust, and you give an information about durability. So for example, if you obtain 97%, so for example 3%, you measure 3% of sawdust, it means you have a durability of 97% because 97 fraction of pellet resisted to this treatment. And so it is a simulation of the life of pellet, which is transformed, which is put into bags, moved, and so on. And so you have information about the durability, because if the durability is very low, when you reach the final user, you have sawdust another way, and it's not useful for a pellet boiler, because it's very difficult to move into screw and to reach the combustion chamber. Just to complete the chemical physical characterization, these are two different complete analysis of two very different biomass. For example, this is 1 year pruning, so these are the pruning you collect during the maintenance of 1 year. And then we have a pellet sample. So, for example, for this kind of biomass, you have very high moisture. You see, 41% of moisture. You have also 2.5% of ashes, and this means less volatile substances, less heating, low and high heating value, and less quantity of carbon, for example, which is 47–48%. Okay, these are some typical values of these parameters. For pellet, you can see a moisture very, very low, 7%, very, very low content of ashes, 0.2%, and this means higher heating value from 19 to almost 20% of high heating value, and it means, of course, higher content of carbon from 47 to 51%. Okay, and this change completely the characteristic of biomass. Okay. Now we can start with energy conversion processes, biomass energy conversion processes. Okay. Would you like to have another break?
It's up to you.
5 minutes, just 5 to 10 minutes, okay? And then we can restart. Okay. After 3 hours, I'm tired, but also you lose some attention, so I prefer to have a break. Okay, see you 5 10 minutes.
Mm-hmm. Is it still recording?
Why do they keep the recordings? do they put on the website?
Yeah, if you can't attend the lesson, you can watch it on YouTube. I think they load them on YouTube, all of them. Last year I couldn't come to a couple of lessons of another course, and they told me to follow the course on YouTube and just take the exam at the end.
Is it like, do they keep on changing, or the courses are still there on it?
I think they are still there. The ones from last year should be still there.
Do you know the name of the channel?
CRB? I'm not sure. Can't remember, but if you go on the website, there should be a link to the online courses.
I don't know. Okay, it's good to know.
But they put them online after months. I can. It's not.
Yeah.
It's not very fast. Yeah, I had to follow this course in what was it? July, and I watched the lessons in September, if I remember correct. I don't know how long did they take to process the video and put it online, but it's not very straightforward.
Because even I missed a couple of classes last year. Firstly, because it's like, at the start I did not know the train timings properly, especially till Perugia University. Till Fontevecchia, okay, I can get. But after that, the buses don't stop. Like,
Yeah,
there was
the
one
public
time.
transports are not so good.
Yeah, there
around
was
here.
one time, like, there was a bus from here to Fontevecchia, so I was planning on taking that. The class ended at 5:30. The bus was at 5:45. I ran from here to there, and then I'm standing there. The bus came in. The bus was entirely empty. If it was full, then I could understand. It was completely empty. The driver saw me, and there was another person who was waiting for the same bus. He saw me and kept on driving. I'm like,
Really?
yeah,
At the bus stop
yes,
here, in front of the
yeah. Like, I'm like,
university.
what happened?
Now, that's strange.
And then I saw his brake lights on. I thought, okay, he'll stop further. And I went, no, he still kept on going. I'm like,
Come on.
then I waited for 1 hour. Then I found out another train. So from that point, I'm
No.
like, okay, I'll go with the train because at
Terrible.
least it's consistent.
I don't know if it was out of order or something like that.
No, there were like 1 or 2 people sitting inside. But
Okay, no, so
other
it
than
was
that, the bus was
working
empty.
normally.
Yeah. The driver literally saw me and then drove away.
Asshole driver. I don't know, it doesn't make sense. But
That's why, like, trains good. At least I know that at this point they will be.
Wow. I mean, it never happened to me, but it shouldn't be like that.
Yeah, it's not like it happened to me just in Perugia. It happened to me in Terni too. But in Terni I can walk around. There it's a small town kind of thing, so I can walk and reach.
It shouldn't happen anyway.
Yeah. Now, in India it happens, but the reason is that the bus is completely full, so they just keep on driving. But I never thought it would happen here.
Yeah, the station Pontevedra is quite far from here.
Yeah.
Linearly, it's not so far. Yeah, but there is the hill. You have to.
Yeah, the roads take a roundabout road.
Mm.
Because the train takes like 5 minutes or even less than
No,
that.
less. Yeah. It's very close. It's like literally over that hill.
Yeah. After Fontainebleau, it starts a climb and okay, you know it's there. The internet is working, I need to check. If the train is still at 2:30.
And what are you studying internally?
So I'm working on two things right now because the hydrate project is going very slow. So I've also started working on fuel cell high temperature corrosion.
What kind of fuel cell? Molten carbonate?
Yes.
Mm.
Like I haven't done any experiments yet, but the plan is there to go ahead with different types of alloys as current collector and then use them into the fuel cell that they already have prepared to see what's the effect. Because like the temperature is high, 800, 600 degrees Celsius plus. So
I also work on fuel cells in
which
the
one?
laboratory down there. High temperature,
The same?
molten carbonate and solid oxide.
Oh, okay. So what are you working on specifically in that, like the formulation or?
We mainly test them, and we test them with, let's say, various fuel compositions, different from ordinary, let's say. I mean, there are some research on classic syngas or biogas from a digester, and what else? Ammonia, for example, or classic hydrogen, or electrolysis. And
who is your advisor? Like, is it Professor Rosa?
no, Professor Vidini.
Okay. So, have you guys done any molten carbonate tests recently? Is it possible for you to get the current collectors?
Not recently. In the past, we worked a lot on molten carbonate. I mean, they worked a lot. I arrived recently, and they used mainly stainless steel.
Yeah, like right now, even internally they are using 316 steel rather than any high composite alloy. I knew that here they make some cathode and anodes, like they formulate it there and then send it here for further processing, and then they come back to
there were some issues with those materials, probably mainly with the matrix.
Yeah, because the reason I proposed this to, I don't know if you know,
you work with Filippo.
I told him like the 316 steel composition, right now it's like some people agree with it that it's good and some people don't. But I worked for an alloy project back in New York. And we did temperatures, we did corrosion testings ranging from like 150 degrees Celsius to 1000 in different conditions, like from wet to high temperature, high corrosive salt to dry, just reduction, oxidation, all kinds of tests. And I came across some alloys which were like in the category of 316 steel, with the composition slightly altered, but they perform like really nice. Because we compared 316, T22 and like all of these variants, regular stainless
In
steel.
the austenitic steel.
And then like there are few which performed really well at high temperatures, but their performance was bad at like low temperature, around 200 degrees Celsius. So that gave me an idea. It's like the salt effect, mostly the salt and the migration effect of elements. That affects a lot. Like some of the few SEM images were like.
So some of the materials perform better at higher temperatures than lower.
like 316 steel, it performed very good at like 200-300 degrees Celsius in a salt induced corrosion environment. But as the temperatures go high, it's performed bad. But then there was a high chrome nickel steel, which is like an expensive aerospace steel. It performed really well at high temperatures, but as soon as we drop the temperature, its performance went bad. There are other issues like mechanical properties, but we were just focusing on that. So that's why I suggested like we should try other compositions, current collector. Because as long as it's same category, conduction issue should not be there. Only the corrosion issue is the main. Because these fuel cells in thermal lab, they are short circuiting due to nickel migration.
Oh.
The nickel spinners, they form, they cut across the cell and they short circuit. So that can be avoided.
So it comes from the steel, basically.
Not the steel, the nickel coating.
Yeah.
Because I came across a specific case where like the nickel chrome, they keep on overlapping each other and induce high corrosion rates over the time of like weeks. And then like it's because you ideally want a protective layer, a protective oxide layer like chromium oxide on top, or any oxide, but it should be protective and consistent. Conductive and consistent. Like, if it's consistent, then there won't be any gaseous diffusion which will attack the substrate. But due to
that's not trivial.
Yeah, but due to differential
Expansion,
rate of growth, they keep on overlapping each other. Like it was a good observation, but then we diverted from. But yeah, that's why I want to do that. So we are right now looking for different current collectors or even past current collectors to observe. Hey, maybe you never told me about this. I'll ask him tomorrow.
What shape, what geometrical shape did you use for the current collector?
Right now it's just a mesh. Yeah.
Woven mesh, metal mesh.
But I wanted to see the past performances under SEM.
Sorry?
I wanted to see like the past alloy performances under SEM in our labs to see how the elemental or how the surface is and what kind of phenomenon is occurring in order to better select the alloy.
Okay. So we were introducing the biomass energy conversion processes, and this scheme shows, I think, the main part of the processes you can apply to biomass. Of course, there are some biomass to bioproduct processes that requires a combination between some of these elementary processes. So here you can see, we start from biomass, of course. Here you can see the main parameters we give us information about the pathway we should move, and you can see moisture in percentage, of course, and the ratio between carbon and nitrogen. Okay, these are, of course, is a very simplified scheme, but very useful to understand the whole strategy for bioenergy conversion. And so we have three main sectors: thermochemical processes, biological processes, and physics processes, then I will explain you what I mean. So, thermochemical processes, we will see three thermochemical processes. I think you shouldn't just know, but we have refresh. The combustion, of course, is the most known. Gasification and pyrolysis. Okay, these are three thermochemical processes. And here you can see where, what kind of biomass we can use for these thermochemical processes, and the biomass has a moisture lower than 50%, and CN ratio higher than 30. So you can also use a percentage expression, and so it means that we have a lot of carbon compared to nitrogen. And of course, this gives you information that you can have a thermochemical process where you need, for the combustion, you need carbon and of course hydrogen for the oxidation process, or also for the other thermochemical process. Okay. Biologic processes. Biologic processes are applied to biomass that has usually a very high moisture content, higher than 50%, and low CN ratio, lower than 30. Okay, and what are the main biological processes? Alcoholic fermentation and anaerobic digestion. Of course, we have other biological processes, of course, for example, aerobic digestion, but for energy applications, we will have a look to these two biological processes. So, alcoholic fermentation or anaerobic digestion. What does it mean, biological process? It means that you use microorganisms to transform biomass into other final products. We are speaking about energy products in general, but in other final bioproducts. For example, in the alcoholic fermentation, you have some yeast that transforms, for example, sugars into alcohol, and you can obtain, for example, bioethanol, which is the one possible substitute of gasoline gas in transport sector. Or, for example, anaerobic digestion. You use another kind of microorganism, which is several families of bacteria that eat biomass and transform it into other final products. We usually use the anaerobic digestion to obtain methane. So you start from some biomass, and now we have a look also to that one, and you obtain methane using microorganisms. And this is a sector. Of course, we work a lot with the thermochemical processes, but we are also taking great attention to biological processes because we are testing, experimenting some biological pathways very interesting for the biorefinery concept. And so there is another important sector. Physics processes is in general is referred to the physics process, for example, is seeds milling, for example. So you have only a physical process. You have a press where you mill the seeds and you obtain vegetable oil. So I don't have many things to say about this process, but of course we will see this process applied in some bioenergy or biorefinery pathway. And these, of course, are some characteristics of moisture, approximately 35% in seeds, of course, because in vegetable oil, which you should don't have more water, and the C on an ratio higher than 35. Okay, but it's characteristic typical of seeds, so there is no other information about these parameters. But here you can see the important difference also in the parameters between the two families of processes. Okay, and it means that for thermochemical processes, you very often you have lignocellulosic biomass, residues biomass, while into biological process you have mainly, for example, amidaceous or sugar biomass, for example, sugar sorghum or grain or something like that, or vegetable residues or zootechnical manure and so on. So these two kind of typology of biomass. But and this is the reason we have also put a lot of attention to this biological process. We can also, and so this is not more right, we can also use lignocellulosic residues. The relative new, because it's in the last 10 years. In the last 10 years, 15 years, the researchers all over the world started to study processes, biological processes for lignocellulosic residues. Why? Why there is more attention to study this kind of biomass for biological processes? Because till now I showed you some biomass that are good for thermochemical processes and some biomass that are good for biological processes. Why you should find pathways that use lignocellulosic biomass also for biological processes? Because it's the answer is very simple. Because lignocellulosic biomass is the most common biomass available in the world, all over the world, and is a biomass that don't go in competition quite ever. Doesn't go in competition with food fields, food crops, or food products. Okay? We cannot eat food or lignocellulosic material because we don't have a system that can take energy from lignocellulosic biomass. But as I said to you, it's a very common biomass because we have a lot of, as we should have seen in the previous lesson, we have a lot of potential raw material we can start from. Okay, from forestry residues to agricultural residues to energy crops on the marginal lands to agro-industrial residues. So there is a lot of biomass that are also sustainable biomass because doesn't go in competition with traditional agriculture and traditional and food for human or also animals feed. Okay. I stay a lot in this slide because it's very important in the now and in the last part of the lesson, and in the next lesson we will go on detail to see combustion, gasification, pyrolysis, alcoholic fermentation, anaerobic digestion, milling, and also a combination of these processes. Because, for example, we will have a look to second generation biodiesel production that or bioheat production that combine different processes, thermochemical and biological processing, or two thermochemical processes in sequence, and so on. So this is a very important starting point for energy conversion of biomass. Focusing on thermochemical processes, which is the first family of process we will see tomorrow and probably in the next lesson. Here is a zoom of the previous left part of the previous scheme, and here you can see, yes, thermochemical family processes: combustion, gasification, and pyrolysis. And then we have a detail of each process. So you can see an important parameter, which is VR, equivalent ratio, which is the ratio between the oxygen you give to the system, to the combustion system, to the thermochemical process, and the stoichiometric oxygen you need for the complete combustion. Okay, what does it mean? If you have a combustion process, which is the I think the well-known process, you have into a lot of system from your boiler in your house, from your engine into your car, and I think every electricity production system and so on. When you have a combustion process, you give to the system more oxygen than he needs for a stoichiometric reaction. So you have, for example, a biomass, for example, biomethane, CH4. So you have to go, you have a reaction, CH4 plus air, okay, plus oxygen, which is in the air, and you obtain CO2, water, and energy, of course. So you have a stoichiometric relation between the quantity of biomass, of fuel you have into the system, and the air and the oxygen you need for the reaction. Of course, the air is still free to have, so of course you give more air than the system need for a complete combustion to be sure that the combustion is complete in every part of the system. This is the equivalent ratio. So for combustion you have an equivalent ratio more than 1, so before you give more air than you need. You have a combustion process, so you transform all the combustion part into carbon dioxide and steam. So the temperature is very high and in the industrial processes will reach also quite 2000 degrees centigrade. Okay? And you have the final products. These are co-products because in general your final product is energy. Okay? So you have co-products, carbon dioxide, water, and ashes, of course, because we have seen that the inorganic fraction of biomass is transformed, not transformed, but you find it into ashes. Okay, this is the combustion. The gasification is a partial combustion. So your goal is not to obtain directly energy, okay, but you want to obtain a gas fuel. Okay, then we will see what is this gas fuel, and then you can use this gas fuel into another conversion system. Okay, and how you can obtain this partial combustion? Giving less oxygen than the system needs for the complete combustion. So there is a very particular value which is around 0.25 of equivalent ratio. So it means that you give only 25% of oxygen needed for the complete combustion. And it means that you have a lower temperature because the combustion is lower, and you obtain some energy that the system needs for maintaining the process. But you are interested at obtaining a gas, usually called syngas, which is your final energy product you want to obtain. Final for this process, because then you can use this syngas into another system to obtain energy. The third thermochemical process is the pyrolysis, which is a process where you don't give at all oxygen, and equivalent ratio is 0. So you don't give any oxygen. You give only heat at temperature around 500 degrees centigrade. There is a range, of course. This is a typical value, but there is a range. And now your goal is only to obtain some energy products, which are another gas that we usually call biogas because it comes from the pyrolysis process. But you obtain also a solid coal, which is named char, and you obtain also a liquid oil, which also can be used for energy purposes if you are able to use it. And of course, some ashes and some steam from the process. Okay. These are the three thermochemical processes. What is the advantage to not have a complete combustion, but to have an intermediate product, or more than one intermediate products into the system? Yes, there are two completely different technologies. Here you have a complete combustion, and then the heat you obtain, you you can use this heat to directly to someone who needs heat, or you can transform heat into electricity using a Rankine cycle, for example, or other cycles we will see during the lessons. But the combustion regards a solid matter in general, which is lignocellulosic biomass. Okay? In the gasification process, you start of course with solid biomass, but at the end of the process you obtain a gas, a syngas, so a gas fuel. And so you can use the gas fuels, for example, in a turbine. So you can put syngas in also in an engine, okay? And so it's a completely different technology from this one. So this one you can obtain heat, or you can obtain, for example, electricity in a Rankine cycle. On the other side, you have, for example, a turbine with this Brayton cycle, or you can also have an engine with a diesel or with a diesel cycle or a gasoline cycle. Okay, and the same for the pyrolysis. But here you have not only to use gas in the same processes we have seen, but you obtain also char, so another solid biomass, another solid fuel, of course has a higher heating value than biomass, but you have to use in another system, and also a liquid fuel that you should also use, or it becomes a waste. And so there is a lot of research in this. Mainly the research is concentrated into these two processes because combustion is known since the Stone Age. So the lot of research is concentrated there. Okay, so it depends on what do you want to obtain from a specific process and what technology you want to use to obtain energy. There isn't a process which is better than another. It depends on many elements you have to put into the discussion. For example, of course, from gasification, if you want to produce more electricity, gasification allow you to reach better efficiency compared to combustion. Okay, because you have higher efficiency. It's not this always true. Also, this is not always true. But in general, you should move to gasification if you want to optimize the electricity production. Okay. Of course, combustion allow to reach higher efficiency if you have a cogeneration system. So if you produce both electricity, but you have also the possibility to use heat for district heating, because we are speaking about industrial system, district heating or something like that. Of course, the global efficiency is high, so it's very difficult to give a classification of the better or the worst system. Pyrolysis is still not so developed, so there are not so many pyrolysis systems in the world, but it's a very promising system to study. Okay. Do you work
I
system?
worked with gasification
Gasification. Okay. Here or in the past?
in the past.
In the past. And what you
Uh,
can see?
we were, as I told you earlier, we were trying to change the feed for an existing system which a company had made. It was like a trailer, like a small scale system on a trailer for farms, where they used to put a pig manure or chicken feces, and then break it down to syngas and other residues. So initially it was working fine, but then they decided to diversify the feed, because initially it was a focused feed. You need to prepare it and then put it. Economically, that was not viable, so they wanted to diversify it and make it smaller. So we started testing different feeds, different conditions, and then there were a lot of issues during testings, and that's why I remember, like, the depressurization. During the depressurization, the ash and sometimes even char also like blocks everything. Then the gas is not clean, or the production of H2CO and those the needed syngas is not high enough. And at some point we were trying to specifically have ethane as our output. The amount of ethane was like really negligible, like not feasible. So then we before I left, we completely tore apart the equipment, and now I don't know how it's going, but now they are like recombining it, doing modifications, changing the conditions, operating procedures, and then maybe in next few years they will get where we want the high efficiency clean gases, everything else.
Yes, you introduced very well some problems correlated to gasification systems. For example, mainly in Italy, we have a lot of problem in the gasification sector, because also the biomass in input must be very must have very particular characteristics. For example, the size of the chips, the moisture, and we have not so good chips with very specific size, with very low moisture. So we have a problem to don't spend too much to have a good biomass in input. And so this is a problem of the low development of the system. And of course, other problems correlated as the output, as you see the gas cleaning, and so it's a very complicated pathway compared to combustion. And so in many cases, the owner of the plant prefer to
we were mostly focused on the feed to gasifier point, like before, what happens before it goes into gasifier, because in gasifier it's straightforward, you can't change much. But before that, all the operations, we changed the moisture content, like we bought dry feed, introduced different moistures, different mixtures, then pumped it in different pressures, different temperatures and everything. It's really complicated. We had many accidents in that, like.
Of course. We are following. I am following this process for I think 10, 12 years, and it was very difficult to find a gasifier older than 1 or 2 years, because maybe in the first months you are able to control the process, to stay, to have a good biomass in the entrance, to control the syngas UX, but after 1 year you have a lot of problem. And so it was very difficult to find a gasifier older than 1 or 2 years. Now, for the first time, very close to here, we have a very small gasifier system which is 50 kilowatts. But this plant is working since 2 years, and till now they have no problems. Of course, they have maintenance during the year, but never had particular problems that stop the machine for 1 month, for 2 months, for example. And this is the first example I have seen. I was in Germany a lot of times to study their gasifier systems, and since they have more, I think, more knowledge than us in the gasifier sector, they also have a lot of problems, and a lot of companies closed because they weren't able to.
Yeah, the team I was working on, they were more focused on digestion or the breakdown part, how the biomass breaks down. Yeah, even now they are like, because we don't have like a big huge plant, we have like the entire system fits in this room. It's like that small, so
Yeah.
that's it.
Good. Okay. So, I think we can finish the lesson in the next class, but I introduced the combustion process. Here you can see I don't comment this reaction because are very simple. But here you can see the main oxidation reaction, because combustion is an oxidation. And of course, in the biomass you have carbon, hydrogen, oxygen, of course, and chlorine, and of course nitrogen and sulfur that contribute to the oxidation and to the combustion of the biomass. And these are the 3 steps we always have into a biomass, because you have to consider that even if you have small chips or small pellet, you have a biofuel which is a volume. So there are different processes in the external part and inside the biomass. So what are the 3 steps of combustion? Very quickly. We have a first stage. We have just talked about for another thing. But when the temperature goes over than 100 degrees, there is a drying step, and so water starts to evaporate and goes down. Then what we have? We have inside the biomass, we have some things like a pyrolysis, because oxygen can reach the internal part of biomass, but the temperature is going up. So you have something like pyrolysis, where where your biomass transforms into liquid part, which named tar, in char and in gas that start to also to exit from the where it finds it can pass. We start also to exit from the biomass. So we have this process, and of course the oxidation process, which is the phase that starts, of course, in the external part where you have oxygen to complete the reaction, and then reach also the internal part where you still have char, tar, and also some gas that wasn't able to exit from the biomass. Okay, this is in a very simplified scheme the 3 steps that we have into every kind of combustion, from the pellet grows into our home to an industrial, a big industrial plant, we have also the same process. And here the same 3 steps, read in another way. So you start from wet biomass. Here you can see a sort of chemical structure of biomass. It's of course is an average value, but for one carbon you have 1.4 hydrogen and 0.7 oxygen. This is an average value of the composition of biomass. So, as you can see, we have the first step when you have the heating and the drying of biomass, and you can see that steam water goes in atmosphere. Then, as I said, we have the pyrolysis part, when without steam, without oxygen, you have a degradation of biomass into, for example, carbon monoxide, which is a gas, in CH, which is something like char, and for example hydrogen, which is another gas, and so you have this pyrolysis. And then you have with air, we name it secondary air, we add combustion, complete combustion, and you obtain the final products, which is CO2, ashes, water, steam water, and for example NOx, and of course energy. Okay. Primary air is for the the first part of combustion, because of course you have this process in general, but when you start with pyrolysis inside the biomass, you just have some combustion, some oxidation in the external part. So this is the primary air that you need for the external combustion. And then you have the secondary air, so some other air you need for the complete combustion of biomass. Okay? Any question? I think we can stop here for today. So from next lesson we will start from here. So we will have a look to starting from a very simple boiler system to we will move to industrial systems. So we have a look to this plant typologies, and then we continue with the program of the course. Okay? Thank you.